In this video, we're going to talk about how the second derivative relates to the graphs of functions, and in particular, how we can use information about the second derivative to classify whether critical points are maximums or minimums. For instance, consider that I have a graph of a function like this, and I have some particular minimum point that's being given, and the minimum down here has a horizontal tangent line. Now, if I move away from this minimum and I consider some point, for example, over here, then I also have a tangent line at that point, and that slope is now a positive if I move my point to the right. And then as I move further to the right, what we notice is that I get more and more tangent lines, and each of them the slope is bigger. That is, as I'm going to the right, the slope, the derivative of this, is getting larger and larger and larger. And so the way I can think about this is that f prime of x, which tells me the slope at a particular point, that this is increasing when I move off to the right. The same happens if I approach my minimum from the left now. For instance, if I talk about a point like this one off on the left here, it has a negative slope. As I move a little bit closer, well, the slope now is less negative, which is the same thing as saying that this derivative is increasing. It starts negative and it's getting bigger and bigger and bigger. As I get closer and closer, my slope is going to be increasing. So the point is that as I move around on this curve, as I go from the left to the right, the slope is increasing throughout. So in the case of when I have a minimum, my slope is going to be increasing at the particular point. Similarly, if I have a different scenario now, I talk about having a maximum, well, then in this case, when I try to figure out what's going on with the slope, it starts at some large value, and then if the slope sort of peters off, eventually it becomes zero at the actual maximum itself, then my slope starts getting negative and steeper and steeper and steeper negative. So what happens here is that my f prime of x is actually going to be decreasing. So let's take this intuition about analyzing the derivative and whether the derivative is increasing or whether the derivative is decreasing, and try to make this a little bit more precise into a test for maximums and minimums. So the first thing I'm going to do is define the notion of being concave up and concave down. Indeed, when a graph is concave up, I sometimes like to put some little eyes, imagine it being a smiley face for concave up. And if I analyze what's happening to the slopes of the tangent lines as you go along are increasing. So f prime increasing is the same as concave up. Likewise for concave down looks like a sad face, and it's kind of funny to say, but nevertheless, the slopes of the derivatives, or the slopes of the function, aka the derivatives, these are getting smaller and smaller. This derivative is decreasing. Now, I can say the exact same thing, it's just I'm going to go up a derivative. When I talk about the first derivative increasing, what we've seen in the past is that a function increasing if it's differentiable is equivalent to the derivative of that function being positive. So in this case, if I talk about the first derivative increasing, that is equivalent to saying that the second derivative is positive. So we restate our claims. Concave up is going to refer to the second derivative being positive on an interval, and concave down is going to refer to the second derivative being negative on the interval. Another scenario can happen, which is when the concavity changes. Or for instance, imagine I'm coming along and I'm concave up, and then it switches and becomes concave down. So at this particular point in the middle, it switches from being concave up to concave down. This is referred to as an inflection point, and an inflection point can happen in one of two cases. One where the second derivative is zero. On the one side it's, say, negative, and the other side is positive, or vice versa. And then the other case is when the second derivative simply does not exist. For instance, we could speak if this one came along and actually went completely vertical for just a moment there. The derivative might not exist at that particular point. If it's straight up and down, you'd have a vertical tangent at that particular spot. So the derivative might not exist, but nevertheless, we still call it an inflection point. Next up, we have something called the second derivative test. And it basically illustrates the intuition that we referred to earlier. Namely, that if I want to analyze whether I have a maximum or a minimum, I find a critical point first. Critical points tell me the candidates to be a maximum and minimum, and then I analyze the second derivative. So in the case, for instance, of a maximum, what we're going to first find is the critical point, the spot where the derivative is equal to 0. And in this case, it's exactly the same as the first derivative test. You find where the first derivative is 0, and those give you your candidates to be a maximum or a minimum. But then I want to look around that point at what is the concavity. And in this case of the maximum, it's a concave down graph. In other words, that the second derivative is less than 0. Alternatively, if you have a local minimum here, you would go and compute the critical points, and that would give you this location down here. And then when you wanted to test to see whether that critical point was a max or a minimum, well, in the case of minimum, it is going to be concave up, or in other words, the second derivative is positive at this point. And then the final scenario here is referring to when the second derivative is equal to 0. And in this case, well, our test simply fails. We do not know which scenario we're in. It might well be in the previous case where the answer is that when the second derivative is 0, it's just neither. But it's also possible that it can still be a minimum. There's an example, for instance, of x to the power of 4th here that looks a lot like x squared, but just sort of flattens out a bit more aggressively. And this spot here is a minimum, but its second derivative at the particular point of x equal to 0, its second derivative is still 0. And so the second derivative test cannot see that it's minimum, despite the fact that it is. So if the second derivative is 0, we have to do further analysis. We cannot simply rely on the second derivative test. Let's see an example. Here I have the function f of x equal to x cubed minus 3x plus 3. It's a cubic. So if I then come along and try to figure out, well, what is f prime of x? F prime of x is just 3x squared minus 3. And if I set f prime to be equal to 0, that is going to imply that x is equal to plus or minus 1. These are my critical points, the spots where the first derivative is equal to 0. But what we want to now do is analyze the second derivative at these two different points to be able to determine whether these are maximums or minimums. So if I can then go and compute what f double prime of x is going to be, well, f double prime of x is just 6x, and 6x is positive when x is positive and negative when x is negative. So I can draw a little chart. I can put in my minus 1, I can put in my 0, and I can put in my 1. The point 0, this refers to an inflection point, a point where the second derivative is going to change its sign. Indeed, to the right, when x is positive, then 6x is positive. So it's positive all over here if I try to go and analyze what's happening to f double prime. But to the left, when x is negative, the second derivative is all negative. And so from this, I can use the second derivative test to say that at the point 1, where you have it being concave up here, we're going to have a minimum. And at the point minus 1, where it's concave down by the second derivative test, we're going to have a maximum. Finally, we might be interested in trying to see whether we can draw sort of a loose sketch of this thing. Well, first, maybe if I plug in x equal to 0, we're going to get the value of 3. And then I'm going to have a 1 put in over here and a minus 1. And indeed, my two critical points, if I plug in 1 to this thing, I'm going to be getting the value just of 1 out. So I can come along, plug in 1, and I get 1 minus 3 plus 3, which is just equal to the value of 1. And if I plug in the value of minus 1, I get minus 1 cubed, which is just minus 1, and then plus 3, and then plus another 3, so I get the value of 5. So if I then try to fill it in, I'm imagining that to the right of 0, it's concave up, so maybe it would come down along here and be concave up to that region. To the left of 0, it's concave down, so it goes all the way up to this maximum and down, and then would continue on in this way. So this is how I can get a loose plot of my cubic by analyzing the second derivative, namely when it is concave up versus concave down, and I can identify that when do I have a minimum and when do I have a maximum.